Hey there, everybody. We are finally to Chapter 8. This is the big one. This is the one with the hypothesis testing, inferences, and all sorts of other great stuff. We're just going to go ahead and jump right on into it. Part 1 is introducing hypothesis testing, and we're going to do some definitions, and then we'll talk a little bit more about what it is exactly that we're going to be doing. So this is a hypothesis. Is a claim or a statement about a property of a population. The property that we are going to be studying with the populations are going to be mean, proportion, and standard deviation. So section 8.1 is an introduction to hypothesis testing. Then we actually do it for these three, and that'll make up sections 2, 3, and 4. So we're going to walk sort of step by step through this, and we're going to start out with we have to make a claim, and our null hypothesis, this is the assumed to be true. So we're going on the assumption, and usually it means that nothing is happening. So we're going to assume it's status quo, everything's the way that it has always been, and then someone can propose an alternative hypothesis, which is here. Sometimes it's written like this. And so we have our null hypothesis, which is our given. Our null hypothesis is always, always, always equal when we state it. And I'll show you examples of what that means here in a moment. The alternative hypothesis is always going to be using one of three. So this is going to be using an equal symbol. These ones are going to have three options: greater than, not equal to, or less than. So those are for our alternative hypothesis, and let's move right into the practice. So we're going to identify the null hypothesis and the alternative hypothesis. The claim is that 20% of adults smoke. Then we have a recent survey of 1,016 randomly selected adults showed that 21% of the respondents smoke. Now notice that these two percentages are different. The whole point of our testing is that difference significant? And we'll be using a lot of fancy math to do that. So first of all, we're using a proportion. We know this because this is our original claim here. And our null hypothesis is going to be that the proportion is equal to 0.2, or 20%. The null hypothesis is going to be that the proportion is not 20%. These numbers will always be the same, but it doesn't say anything about bigger or smaller or anything like that. Let's do another claim. The proportion of baby girls is greater than 50%. The latest actual results show that among 945 babies born to couples, 879 were girls. I just want to give us an idea of what that means. So we're going to take 879, and divide that by 945. 945. Now, 93% were girls. This sounds like a made-up statistic to me. But 93% compared to 50%, that is significant. So how would we write that up as a null hypothesis? Well, this one's about a mean. I'm sorry, this is a proportion as well, proportion. The null hypothesis is that the proportion of baby girls is 50%, or 0.5. The null hypothesis is that it is not, or that it's larger, pardon me. So they want to know, the claim is that it's greater than, so P is greater than 50%. And based on the data that we have here, I tend to agree. 93% is out of control and not very realistic. So that's our first step in all of these major hypothesis testing is what is the null hypothesis, what is the alternative hypothesis. Just a quick side note, our justice system is based on the same thing. So the null hypothesis is that the person is innocent. That's presumed innocent until proven guilty. So the claim, so this is the claim here, that the prosecution makes is that they say that the person did do something, and so the burden of proof is now on them. And that's the way it is here. There's an assumption, And then there's something that says, I don't think that that's right. The burden of proof is on the person making the alternative claim in this case. So we're going to move on. Oop, too far. There we go. Now we're going to select a significance level. This should be done prior to testing. This actually, when people say you can cheat with statistics, that's what they're talking about, is setting this. Our alpha is going to be our significance level, meaning how sure do we want to be about our final results. So as we're looking, in that is the Greek letter A, alpha, and we talked about alpha before. We get that from the confidence level. Usually alpha is given to us in these problems, so we don't have to select it. Now, if we were doing real research, we would have to select an alpha. And the common alphas are alpha is 0.01, 0.05 for 5%, or 0.1 for 10%. So 10%, 5%, or 1%. 1% being the most sure. And on to step 3. This is our test statistic. The test statistic is a value used in making a decision about the null hypothesis. Now, this is based on, the test statistic is based on data. So if we look at some of these previous examples, the data would be the 879 over the 945. So that would be the data that we would be comparing with in that case. We have formulas for all of these. Don't worry, all of our calculators do all of these for us, except for this last one here. There are times when we'll have to do that manually. So the first one's a proportion. And the p hat is the sample test statistic, pardon me. Just plain old p, that's what's given as part of the problem, as part of the assumption. That's the p that's going to be used there. Q, if you recall, is Q is 1 minus p. That's the complement of p. Now we have 2 of them for mean. And here's the big deal with that one. We are going to use a t distribution for mean if sigma is not known, meaning the population standard deviation is unknown. If it is known, which in real life it rarely is, then we're going to use a z distribution. And you can see the 2 formulas are very similar. If sigma is known, then we use it here. Otherwise, we use the sample standard deviation. Otherwise, the 2 formulas are identical. And again, as n gets really, really large, these 2 formulas actually get closer and closer to each other. The fourth test statistic is the chi-squared. That's when we're doing standard deviation. And you can see the formula right there. For sure to use this one, a requirement is that the original data has to be normally distributed. So exciting. All right, so next part. So we're going to practice finding the test statistic. And I'm going to go ahead and read this. 3/4 of all adults believe that it is important to be involved in their communities. Based on a poll of 1,021 randomly selected adults, 89% believe that it is important to be involved in their communities. Okay, a couple of things here. We need to first establish our null hypothesis and our alternative hypothesis. This is a proportion because 3/4, and we have percentages in there. So 3/4 is the same as 0.75. And it doesn't say that it's going to be more or less, so this is going to be a not equal to. Unless it specifies, it's going to be a not equal to. And with a p, we're going to be using this formula here. And let's label real quick what we have. So we have p already is right here. P hat, it is 0.89. N is 1,021. Real quick, Q then is 1 minus 0.75 or 0.25. And so let's get our test statistic. So Z is going to be P hat minus P over the square root PQ over N. So this is 0.89 minus 0.75. So Z is going to be positive in this case. Over the square root of 0.75 times 0.25 all over 1021. Let's figure out how we're going to do this. So in parentheses, 0.89 minus 0.75 divided by square root. Now your square root, you may need to use parentheses. Mine keeps everything on the square root very nicely. 0.75 times 0.25 divided by 1021. And again, you may have to be extra careful with your radical. If it has a parenthesis, you'll have to close parentheses and things like that. And this gave me a Z of about 10.33. That means it's 10 standard deviations away. That's really large, and we'll talk about what to do with that. This means that the alternative hypothesis is, yeah. Anyway, we'll get to the meaning of all this here in just a moment. So make sure you practice this with your calculator a couple of times. Right now we're just finding our test statistic. We don't know what that means yet. Next up, we have a claim for adult females. The standard deviation of their white blood cell counts is equal to 5. The random sample of 40 adult females has a white blood cell count with the standard deviation of 2.28. So this one's about standard deviation, so our null hypothesis is going to be about standard deviation. In this case, they're claiming it's equal to 5. The alternative is that it's not. Now we have sigma, we have S, we have the standard deviation from a sample, which is the 2.28, and we have that N is 40. And again, I want to point out, back to this table here, we have this one here. So I'm just going to plug everything in. So chi-squared is equal to 40 minus 1 times 2.23 squared over 5 squared. Here we go. So I'm going to get 39 times 2.23 squared equals divided by 25. And there's my test statistic. You know what? I wrote that down wrong. That should be 2.28, not 3. So I'm going to redo that. So 39, that's the 40 minus 1, times 2.28 squared equals divided by 25. That matches my notes better. And again, make sure that you practice as well with your calculator. For adult females, their mean white blood cell count is equal to 8. So now we're talking about mean. A random sample of 40 adult females has white blood cell counts with a mean of 7.15 and standard deviation of 2.28. So this is, and this gets confusing. So here's our standard deviation. Now to be clear, this is a sample standard deviation, not a population standard deviation. The significance of that is if it's a population standard deviation, we use a Z. If it's a sample standard deviation, which this is, we're going to use a T. So we're definitely going to be using a T test statistic in this case. So let's write our null hypothesis. That's that the mean is 8. The alternative is that it is not 8. So we have mu, we have x bar, that's our sample mean, which is the 7.15. And we have the sample standard deviation, which is S, not sigma, 2.28. So this is going to be definitely a t test statistic. So t is going to be x bar minus mu over standard deviation divided by root n. So let's plug in what we have. We have 7.15 minus 8 divided by s, which is 2.28, divided by, we didn't write down n, was 40. Now I'm going to be extra careful with my calculator on this one, especially with this weird fraction in the bottom here. So in parentheses up top, 7.15 minus 8, close, divided by, parenthesis, 2.28 divided by the square root of 40. Again, you'll really need to practice this a few times to get good at this. So this gives me negative 2.3578. So that means it's more than two standard deviations away. Again, we don't know what to do with these test statistics yet, but we will by the end of what we're doing today. All right, so again, make sure you practice with your calculator on these. So the test statistic alone does not give us enough information to make a decision about a claim being tested. For that decision, we can either use the p-value or the critical value. These are dominated and come from our alpha. Now, both approaches require that we determine whether the hypothesis test is two-tailed, left-tailed, or right-tailed. And to determine that, we're going to look at these two graphs. Oops, it looks like this got cut off down here. This should be that the alternative hypothesis is bigger than. So when we use a two-tailed test, specifically when in the null hypothesis or the alternative hypothesis it's not equal to, when it's less than, it's a left-tailed test. When it's greater than, it's a right-tailed test. And that's basically what these say here. And let's talk critical region. Critical region. The critical region, sorry about that, that's pretty bad, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. And that's very specific language, we'll come back to that. But again, if it's less than in the alternative hypothesis, it's a left-tail test. If it's not equal to, it's a two-tail test. And if it's greater than, then it's going to be a right-tail test. Let's kind of see what we mean by that. And we're going to start with the p-value method. And then we're going to try to put all of this together. So to find the p-value method, and let's get my colors right. What we're going to do is we're going to find the p-value, we're going to find the area beyond the test statistic and then use the procedure. So here, so let's say our test statistic ends up being here. Our test statistic. Well, this area, to the left in this case, this is a less than case it looks like, is called the p-value. And you're going to use your skills that you learned on using norm CD to come up with that. Now, if it's the other way, and you can see this is a left tail test, this is a less than. If we have a greater than, let's say we're here, here's our test statistic. And it'll be here. So this is clearly a greater than. Once again, this is the p-value. The third case is here, where we split it maybe, and we actually have, even though we only have one test statistic, it gets split. We'll talk more about that as well. And so actually the p-value, this is the not equal to case. So the p-value is that plus that. And let us practice that. All right. Use the given statement to find the p-values. The test statistic is 2 is obtained when testing a claim that p is bigger than 0.5. So this means that the null hypothesis is p equals 0.5. The alternative hypothesis is that p is bigger than 5. That is going to be a right tail test because it's greater than. You can see that there. So take this down here, so this will be 1. So we'll be here. So this is 2, right? 2. So we want to find the p-value. So I'm going to do norm CD, and I'll do the TI version. Actually, it doesn't matter because I won't do the either. So the left boundary, if you remember, in this case is 2. The right boundary is a big number. Go to distributions, normal CD, and that's going to be 2, comma, and then a big number. And there it is. That is our p-value. Let's see, I got it. It makes you practice it as well. 228. And eventually what we'll do is we're going to compare this to our alpha. So it's all going to kind of come together. For the second one, they're saying the null hypothesis is p equals 0.6, making the alternative hypothesis, p in this case, they say is less than 0.6. Let's see what that means. So here we have our p-value. I'm sorry, that our test statistic is way back here. I'm guessing this is going to be a very small number. -3. So again, this is the p-value. And the p-value is going to equal, in this case, normal CD. In this case, -9999999, comma, -3. -3. Yeah, that's a very tiny number. So I get 0.0013. If you're ever not sure how many digits to round off, 4 is often a good number to use. All right, we have our third scenario. And here we have that the null hypothesis is that p is equal to 0.25. Our null hypothesis, our alternative hypothesis, is that it's not equal to. Now remember, this is going to give us a two-tail. So we are here. Now this is at negative 1.23. So you can see the area, I'm going to be missing it when I do it. So here's the p-value is this plus this. So we'll talk about what that means here in just a second. So the p-value this is going to be negative 99999, comma, negative 1.23. So this is negative 99999, comma, negative 1.23. Now this gives us 0.1093, but we have to times 2. So our overall times 2. So this is actually half the p-value. So the total p-value is going to be about 0.2187. So it's easy to forget that. And I believe there is a test question that does do that. That's using the p-value method. The critical value method is a little different. Critical value method says we find the critical value which separates the critical region. And we'll deal with that here in just a moment. And we're going to do the same examples here. Except now we're going to look for a little bit different. So all the null hypothesis and alternative hypothesis are all here already, so I'm not going to rewrite those. I actually want to optimize my space here. So let's start with number 1. So here we are, once again. Z equals 2. And we're not going to care what the p-value is in this case. We're going to come up with the critical region. Now, this one has an alpha, and all of them will have an alpha. And because we have a greater than, that means it's right-tailed. So this means that alpha is going to be on this side here. So to find alpha, or actually to find not alpha, but the critical value, I actually have to do inverse norm for that. And remember, inverse norm is only area to the left, and this area is going to be to the right. So it's going to be 1 minus when I do inverse norm. So it's going to be 1 minus 0.05, 0.05. And you can see my critical region, 1.64, is here. And you can see that's actually going to have its own area as well. And that's going to actually be the two things that we'll be checking. So let me find the p-value real quick. Oh, we already found the p-value for number 1. It's right here. So the p-value is about, that's from up here, 0.0228. And our alpha is 0.05. So the p-value method, which is the method that we just did up here, is going to compare these two. And then we're going to make a comparison. So which one's bigger? Well, it clearly looks like the red is bigger. And I should have written that in red. It looks like that area is definitely bigger. But the critical value method is not comparing that. It is comparing the test statistic in this case. So the test statistic, which in this case is 2, comparing that to the critical region. The critical region, which is alpha. Not alpha. It's the critical value, which is the 1.64. And now we don't know how we're going to compare those, but these are the two different ways. So one is comparing area, the other one is comparing the test statistic to the critical value, which is the boundary for the critical region, which is what the red is, the alpha. All right, so we're doing this in layers. Let's try number 2. Once again, same null hypothesis up here as before. This one is less than, so this will be a left-tailed. All right, so we are given information. We're going to assume that the alpha is the same for both. So in this case, it'll be negative 1.64. Once again, if you need to. And this is 0.05, just like this was as well, 0.05. The blue was only this. So we have our test statistic, which is at negative 3. That's way over here if you remember, negative 3. And what we can do is find that area to the left by using norm CD, which we already did up here. So we know that that area is 0.0013. So again, that's comparing the two areas. That's the p-value way, the first way up there. The other one is to find the test statistic, or to use the test statistic and the critical value. And it's the same as this one, is how I got this one, but I'll show you how I got it anyway. So inverse norm of, now remember it's area to the left, so it's just 0.05, and you can see we end up with the same negative value that we did here. So now we have area compared to area, or the test statistic compared to the critical value. So once again, this is the critical value set by alpha, and this is the test statistic. I should use the blue to be consistent. All right, and our third one. Going to be our two-tail. So now our alpha gets split up as well. So the area here is 0.025. So that's that 5% split up in two. Then the other half is here. And so we have new critical values. So I'm going to do area to the left here. So inverse norm of 0.025. That'll give me the left one here. Oop, I hit the wrong thing. So inverse norm 0.025. So the left one is negative 1.96. This one will be a positive 1.96. I will show you. Inverse norm, again, of 1 minus 0.05. Area to the left. Whoop. I typed that wrong. 1 minus 0.025, pardon me. And you can see that it is the same. This is versus the test statistic, which we got, which is negative 1.23. In this case, you can clearly see that one is bigger than the other. All right. Clear as mud, right? All right, so as we move on to the last page. So once we get all of that information, what do we do with it? How do we interpret what to say with it? Well, we have to make a decision. And our choices are to reject the null hypothesis or fail to reject the null hypothesis. Those are our options. Now, back to the courtroom analogy. Notice that we don't say that we accept or whatever. We either reject it or we fail to reject it because, like in a court of law, the final verdict is not innocent or guilty. It's guilty or not guilty. So you can kind of see a parallel to that there. And the more you think about it, the logic is very sound on that kind of stuff. So if the p-value is less than alpha, then we're going to reject the null hypothesis. If it's bigger, this is the p-value method, then we're going to fail to reject the null hypothesis. Critical value method. If the test statistic is in the critical region, we're going to reject the null hypothesis. If the test statistic is not in the critical region, then we're going to fail to reject the null hypothesis. Let me give you a quick diagram of what we mean by that. So if we're here, and so if this is the critical value, and this is the test statistic, you can see the test statistic is in the critical region, right? Critical region is here. So if it's in the critical region, we're going to reject the null hypothesis. If it's the other way, again, this is the critical value. If the test statistic is not in the critical region, then we're going to fail to reject the null hypothesis. And now we have the wording. And I'm going to try to make it so that all of ours are only this one. In fact, I'm not even going to go through this one. It makes it a little confusing. Okay, so our final statement is a full sentence. And yes, you have to write a full sentence or type one, or if it's in a computer, you'll have to click the right one. And that actually can get a little tricky. So if we reject the null hypothesis, then we say there is sufficient evidence to reject the claim that whatever the claim was. If we fail to reject the null hypothesis, then we say there is not sufficient evidence to reject the claim that, and then you state the claim. So we're going to practice. All right. So one, the original claim is the percent of M&Ms is greater than 5%. I don't remember what that's in reference to. Maybe it's trail mix or something. So let's start with one. State the conclusion that supports, that addresses the original claim. So the hypothesis test is with a p-value of 0.001. Again, we're assuming a significance of 0.05. Now we're going to compare those two. We're going to say that the p-value, which is 0.0010, is smaller than our alpha, which is 0.05. So if our p-value is smaller than our alpha, p-value is smaller than our alpha, we are going to reject the null hypothesis. And when we reject the null hypothesis, if we look up here, we say there is sufficient evidence I said that backwards. This is the one I don't want to do. This is the one that we're going to use, is this second one here. So there is sufficient evidence to support the claim that, this is when the claim is on the alternative hypothesis. I'm going to always try to shoot for that, which on these I'm going to assume that that's true. So when we reject the null hypothesis, we say there is sufficient evidence to support the claim that the percent, sorry, I'm saving space here, percent of M&Ms is bigger than 0.05 or 5%. So we reject the null hypothesis. There is sufficient evidence to support the claim. Number 2. Women have heights with a mean of 160 centimeters. The hypothesis test is that the p-value is so p-value is 0.0614, which is larger than our alpha, which is 0.05. So we're going to fail to reject. The null hypothesis. So there is not sufficient evidence to support a claim of the M&Ms, that the proportion of M&Ms is bigger than 5%. And this video is getting a little long, so this last part, just real quick. Basically, in a court of law, there are 2 ways to make mistakes. One way is for the person on trial who actually is innocent, they didn't do the crime, and they are found guilty. That's a mistake. The other mistake is that the person actually is guilty and is found innocent, or not guilty, I should say. Those are the 2 types of errors. So type 1 error means that we reject the null hypothesis, and the type 1 error is that we're rejecting the true hypothesis when we shouldn't. So that's kind of like the courtroom case. And if we fail to reject the null hypothesis, if it's the correct decision, then it's a type 2 error, meaning that we're failing to reject the null hypothesis when we should. Whew, that was a long one. Chapter 8 videos are going to be long.